This next lesson is going to be on inverses. The inverse of a function is the reverse of the original function. The inverse of a function undoes what the original function has done. If the original function is defined as y equals f of x, then the inverse of the function is y equals f inverse of x. This -1 up there looks like an exponent. It does not operate as an exponent. It's just a symbol for f inverse. If the point AB is on the curve y equals f of x, then the point BA is on the curve y equals f inverse of x. As we will see, the way that we determine the inverse algebraically is to switch the x and y variables in the defining equation of the function. Now, why are inverses important? They're important because sometimes it's helpful to switch the independent and dependent variables of a function. Well, when would that be, you might ask? Well, for example, suppose that the Lenarduzzi Paving Company charges $10 per square foot for interlocking paving stones plus a $50 delivery fee. Letting x be the area that Tom wishes to cover in square feet and letting f of x be the cost to Tom, we can state that f of x equals 10x plus 50. Building a table of values, we get our independent variable x has these values, our dependent variable has the values 10x plus 50, which are in the second column. Now, this table of values is useful when we know the area that we wish to cover and we want to know the cost. But suppose there's another situation where an individual knows how much money they have and they want to know the size of the area they can cover. In that case, we'd want to switch the formula around so that we input the cost and receive the area as output. Well, how do we do that? What we could do is we could let y be f of x, so we could write y equals 10x plus 50. Then we could switch the x and y so that x was equal to 10y plus 50, then solve for y. We'd subtract 50 from both sides, and then we would divide both sides by 10. And so using the formula that y is equal to x minus 50 quantity over 10, we would be able to let x equal the amount of money that the person has on hand, and y would be the area that they could cover. So what's the method to determine an inverse? Step 1, rewrite the function expression substituting y in for f of x if necessary. Step 2, switch the positions of x and y in the equation. Step 3, solve for y. And step 4, substitute f inverse of x in for y. So for example, let's say we have the function f of x equals 3x minus 7, and we want to determine the inverse of that function and state the slope and y-intercept of the inverse. Well, we can let y equal 3x minus 7, switch x and y, and then we have x plus 7 equaling 3y. We can then divide both sides by 3, and we can then substitute f inverse of x in for y. We've got this new defining equation for y. We can substitute f inverse of x in for y, and we can say f inverse of x equals x plus 7 quantity over 3. Well, rather than leave it like that, it's nice to say that that's the same as 1/3 times the quantity x plus 7, and then we can say that that's equal to 1/3 x plus 7/3. And this tells us that the slope of the inverse is 1/3 and the y-intercept is 7/3. It's usually preferable to write an expression like that in polynomial form rather than in rational expression form. So suppose we're given a function f where the points in the function are 2, 3, 4, -9, and 5, 11. We want to determine the points in f inverse, and we want to state the domain and range of both f and f inverse and determine whether f inverse is a function. Well, to determine f inverse, we simply switch the x and y coordinates. So 2, 3 becomes 3, 2, 4, -9 becomes -9, 4, 5, 11 becomes 11, 5. So we can say that the domain of the original is 2, 4, 5. The range of the original function f is -9, 3, 11. The domain of the inverse is -9, 3, 11, and the range of the inverse is 2, 4, 5. Note that the domain of f is equal to the range of f inverse, and the domain of f inverse is equal to the range of f. That will always be true. So in red, we have this really nice statement. The domain of f is always equal to the range of f inverse, and the range of f is always equal to the domain of f inverse. That's pretty cool. This is very logical. Since the inverse involves switching every x coordinate with every y coordinate, Therefore, the effect of that is to switch the set of all x coordinates with the set of all y coordinates. In other words, the effect is to switch the domain and the range and vice versa. Now for part C, we see f inverse is 3, 2, negative 9, 4, and 11, 5. Every possible x coordinate is paired with only one possible y coordinate. Therefore, f inverse is a function. Now, how about if we're given that the function f contains the points negative 7, 6, negative 2, negative 1, and 6, negative 1. Let's determine the points in f inverse, the domain and range of both f and f inverse, and determine whether f inverse is a function. Well, to determine f inverse, pretty easy. We just switch the x and y coordinates of each of the points. So we get 6, negative 7, negative 1, negative 2, and negative 1, 6. Cool. The range of the original function is negative 7, negative 2, and 6. Those are just the x coordinates of the original function. And the range is negative 1 is the set of negative 1 and 6. Now you might be tempted to say 6 comma negative 1 comma negative 1. But remember, you only state each individual value once, and you state them from least to greatest. Now, referring back to what we said f inverse was, the domain of f inverse is negative 1, 6, and the range of f inverse is negative 7, negative 2, 6. Well, f inverse is not a function, because when x is equal to negative 1 in f inverse, the y coordinate could be negative 2 or 6. Remember, this is f inverse we're talking about. So, from step C, the moral of the story is, as we can see, if f is a function, then the inverse f inverse may or may not be a function. And let's try graphing the inverse of this function here. So we're given the function y equals f of x, and we want to graph the function y equals f inverse of x on the same Cartesian plane. So what we can do is determine the coordinates of the key points on the graph of y equals f of x. Now, on a test or in a homework assignment, you don't have to actually show all of this. But these are the key points on the function. So what we're going to do is switch the x and y coordinate and put each of those in red. And there they are. Now, you can... from here, we see that the original function has a line segment from negative 5, 3 to negative 1. Actually, this should say negative 3, negative 1. So the inverse will have a line segment from 3, negative 5 to negative 1, negative 3. There's a little typo on here. Okay, so we put that in. Okay. Then the original function has a line segment from negative 3, negative 1 to 1, 2. Right there. So ours should have a line segment from negative 1, 3 to 2, 1, which would be right about there. Okay. The original function goes from 1, 2 to 3, 2. So while going through 2, 3. So the inverse will go from 2, 1 to 2, 3 while going through 3, 2. So look in the upper right quadrant there, and you'll see the inverse looks like that. And finally, because the original function shoots through 5, 1 with an arrow, this inverse will shoot through 1, 5 with an arrow. Okay? Now, that's what the inverse of the function looks like. And something interesting is that the inverse of a function is always a reflection of the original function in the line y equals x. So if we graph that dotted diagonal line y equals x, we see that the red and the blue are reflections of each other. And that is the end of the slideshow.